Hello and welcome to this Loft talk about microservices. In this talk we want to cover the topic of high availability and how we can use microservices to achieve a resilient and robust systems architecture. A few words about myself. My name is Robin. I'm a technical consultant at Devo A Cloud Germany. Professionally, I like distributed systems and working with cloud computing, cloud systems. I'm really interested in the field of fog computing and edge computing. And I'm personally based in Berlin. In my free time, I really like to go climbing and bouldering, read a book, or ride my bicycle. In the previous talk, we already covered the traditional architecture and why and how we might redesign this architecture to a microservice pattern to achieve a loosely coupled and highly scalable application. And this is all well and good if we look at pictures like this, where everything is neatly ordered and simple to understand. But in reality, it usually goes like this. This is a picture that Werner Vogels tweeted after someone asked him how the microservice system at AWS looks like. And if we look at something like the system depicted in the picture, that almost looks like a living organism, it feels obvious that Werner Vogels also says everything fails all the time, and we just need to accept this as a reality and design our systems accordingly. And the outlook of this talk is as follows. I grouped the talk into 3 topics. First, we want to have a look at patterns for resilience. What can we do on a service level to build resilient and robust building blocks for our microservices systems? Then we will have a look at what role orchestration plays in the role and in the way to reach scalable and highly available systems. And then I want to finish by motivating the need for systems that automate and make deployment and infrastructure deployment repeatable. So first, let's have a look at patterns for resilience. The dictionary defines resilience as an ability to recover from or adjust easily to adversity or change. This is exactly what we want from our microservices. And in the beginning, I want to establish a shared mental model how we can look at our microservices and our microservice systems to take it from there. So the first thing I really want to point out is that we have to see as our microservices as an ephemeral system, meaning that they last a very short time only compared to the traditional monoliths that run for a long time, either until they get shut down or until they crash, but usually they stay where they were deployed. This is not the case for microservices. Usually they really start and stop and get moved and restarted to suit the needs of the application and to optimize hardware utilization to the maximum. So it's important to see the services exactly as such, as a logical component that gets deployed but might be moved at any point. Another view I would like to motivate is to prevent the misconception that microservices are fully independent from each other. That is to some extent certainly the case. So we can work on the services independently, and we can also deploy the services independently, but nonetheless they they play together as a system, and I want to motivate that we should actually understand the architecture as a system as a whole and not just as its building blocks. And if we look at the system and not at the individual components, we understand that we need a way to have an overview about the system, and we need ways to understand how the building blocks of this system play together and how they perform, and need to make sure that they are in an operating state. And this is why monitoring and observability are a key component of any microservice architecture and are really required to enable a highly available system from the start. So let's have a look at actual patterns on a service level. I already motivated the need for monitoring and how could we actually implement this on a service level. Things like health endpoints has been established, or are an established way to communicate to the rest of the system how a single microservice is doing. And usually we expose an endpoint that can be contacted by other systems to ask the individual service about its state, see if it's up and running and if it can take more traffic or things in that area. So this is the first thing. We as a service should expose information to the rest of the system how we do, basically. And then to extend this, we also need to expose our metrics, extending from just communicating that everything is well. We want to have more insight on how our hardware utilization might be, or what are the time needed is to finish a request. And this is what we expose metrics for. We could either also expose them via an endpoint that can be contacted by other services to query data from, or as depicted in this picture, we run on top of a platform that offers the functionality of collecting our metrics and logs and store them in a central storage to be used for later steps. The last service pattern I want to cover in here is the externalization of configuration, and we already saw that our services are short-lived and might be moved, and to add to that, usually services talk to other endpoints, and to be flexible in how we configure this, it's recommended to externalize that configuration and not store it in the service itself, because if we want to change the runtime configuration, that would require us to rebuild the whole service, and by externalizing that, we can change configuration while the service is running without the need of restarting the service. This as a quick overview what we could do on a service level to improve the resilience. In the second part of the presentation, we want to have a look at orchestration and how orchestration can help us to scale and provide a highly available system. And our services need an orchestrator to arrange or combine our services so as to achieve a desired or maximum effect. I really like the dictionary definition of the word. It really describes what an orchestrator does. So we have the picture from the previous slide with our services that run on some hardware that are observed by this monitoring block to have an overview of the state. And the role of the orchestrator is then to manage these nodes and collect these metrics and act on them. And the orchestrator also takes care of scaling out, scaling in, and just managing this underlying compute infrastructure as needed. Let's have a look at usual functionality that such orchestrators provide and start with auto-scaling in a horizontal way. Let's imagine we have our red microservice, and this service now experiences increased load, and the orchestrator notices that by using the provided metrics and monitoring facilities, and then is able to react on that load change by scaling out the service onto different nodes to handle the increased load. And from an application view, this is still one logical deployment, but spread out over multiple instances to serve more traffic. This would be the horizontal way of scaling. There's also the way of vertically scaling. So we have our green microservice here, and we notice that for larger requests we need more compute power on an individual service level. So the orchestrator could also increase the provided hardware or provided compute power for that service specifically and scale that one instance vertical in size. So we have these two patterns of auto-scaling to react to load. Now we will have a look at a pattern called node affinity and anti-affinity, which helps us in building an architecture that is resilient and can endure node failures or even availability zone failures. Just shortly explained what node affinity does. We can attach labels to our compute nodes and specify which service is allowed to run on which node, and with this mechanism one could imagine that if we deploy a database to provide data storage for our microservices, we wouldn't want to have two replicas of the same service on a single node, because we would lose resilience that way. If the node crashes, we lose both replicas. So with these node affinity and anti-affinities, we have a way to tell the orchestrator how to split the system in such a way that we can endure node failures, but also availability zone failures by spreading out our replicas over multiple physical nodes. The next pattern I would like to present is the mechanism of the rolling update. So we need a way to bring changes of our microservices to the cluster, ideally without interrupting the availability of the system. And what orchestrators usually provide is a thing called rolling update. So in this example, we will update our red microservice. Currently we run version 1, but we want to deploy the version 1.1. So what the orchestrator does, it starts the new software increment and waits until it is available using things like health endpoints and metrics, and only after the service is available, traffic will be routed to that service, and the orchestrator will then update bit by bit each deployment of that service from version 1.0 to version 1.1, and in that way we can deploy a new software increment without any software downtime, and also with the safety that if we get stuck in a deployment, we still have running services of the old version. So far, some patterns and some mechanisms that the usual orchestrators provide, and as it usually goes in the cloud, we can decide on what layer of abstraction we want to work. So we can go from left to right if we want to have a full control over the orchestration and the platform, the current industry standard to use is a Kubernetes as the orchestrator engine, and on AWS we could use an EKS hosted solution to have full control over our orchestrator and our node affinities and things like this. And if we go from left to right, we can give away more and more responsibility to the cloud provider, from ECS to AWS Lambda functions. More and more of the patterns I just described, like the rolling update or the node affinity, will then be taken care of by the software as a service solution. And by that approach, we can select the orchestrator that fits our application need best. And in the first two chapters, we saw that there are really a lot of moving parts in a microservice system. And to be able to adapt and work with this efficiently, it's really important to automate the way we deploy and manage things. Just another quote from a famous computer science researcher, Leslie Lampert, to motivate this. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. And this can happen in distributed systems all the time. And therefore, it's really important to think automation as an important building block in reaching the goal of highly available systems. And one of the parts that we need is the pattern of continuous delivery, really the defined ways of how we build our services in infrastructures, code pipelines that build the microservice increment and then bring the increment to the platform using the orchestrator and pipelines in an automated way. So we can repeat them and we can deploy quickly without manual effort. And this holds also true not only for the way how we get the services into the cluster, but also how we bootstrap the infrastructure as a whole. And here it's also very common and a good industry practice to describe your platform also using code, following the infrastructure as code pattern to achieve the same goals, to be able to easily start and redeploy your whole application stack from the orchestrator level to the service level. So in this talk, I tried to show you the building blocks that I find important to reach a highly available microservice system. First on a service level, then motivated what orchestration can do for you, and then tried to motivate as well why automation is, in my opinion, also an important building block of this whole systems design. I hope I could give you some interesting insights, and I thank you for your attendance.